Okay, so today we're going to look at the voting theory chapter. The first, we need to talk about preference scheduling. A preference ballot is a ballot which the voters rank their choice in order of preference. So here we have a vacation club is trying to decide which destination to visit, Hawaii, Orlando, or Anaheim, and here's their votes. Here we list all of the voters, and then down this way is their first, second, and third preference. Okay, now these individual ballots are typically combined into a preference schedule, which shows the number of voters in the top row that voted for each option. So let's just look at this first one here, AOH. You have Bob. And he's the only one. So that's the one, and so forth. So basically what we've done here is by totaling the vote counts across the top, we can see that we still have 10 total votes. So the first voting method we're going to learn about is called plurality. Now this is the one most people should be familiar with. This tends to be how most of our elections are run. Not specifically, but this is the closest method we'll learn to how our elections are run. So in the plurality method, the choice with the most first place ballots is declared the winner. Ties are possible and would have to be settled through some sort of runoff vote. So again, looking into our election from above, we have the performance or preference table. For the plurality method, we only care about the first place options. So this is all we're looking at. Yeah. Is the first place right here. And what we want to do is figure out who has the most first place votes. So we have Anaheim, which has this 1 here and this 3 here, which is 4. Then we have Omaha, which has this 3 here. And then we have Hawaii, which has this 3 here. So in this case, Anaheim would be the winner by the plurality method. Now let's look at another one here. 3 candidates are running in an election for county executive: Goings, McCarthy, and Bunny. Voting schedule shown below. Which candidate wins under plurality method? So again, we're tallying up the number of first place votes they each have, and the one with the most of them would be the winner. So let's see what we have here. Goings, we have there, which is 44, right here. Goings again, which has the 14. And Goings again has the 20, which gives us what? 78? So Goings has 78 first place votes. Okay, now we look at McCarthy. McCarthy has the 70 here and the 22 here, which is 92. Then lastly, we look at Bunny, who has the 80 here and a 39 here. This is 119. So in this case, Bunny is the winner. And that's how it's done. So there can be some problems with this. The election from example 2 may seem totally clean, but there's a problem lurking that arises when there are 3 or more choices. Looking back at our preference table, how would our members vote if they only had 2 choices? Anaheim versus Orlando. 7 out of 10 would prefer Anaheim over Orlando. Anaheim versus Hawaii, 6 out of 10 would prefer Hawaii over Anaheim. And Anaheim just won the election, yet 6 out of 10 voters, 60% of them, would have preferred Hawaii. That hardly seems fair. So that brings us to Marquis de Cordescent, French philosopher, mathematician, and political scientist. And he wrote about how this could happen in 1785. So we name our first fairness criteria after him. Fairness criteria are statements that seem like they should be true in a fair election. So if there is a choice that is preferred in every one-to-one comparison with the other choices, that choice should be the winner. And we call this the Cordescent winner or Cordescent candidate. So let's look here, back to our first election, and we look at each of the pairings. So Anaheim versus Ohio or Omaha, Anaheim versus Hawaii, and Omaha versus Hawaii. So Anaheim versus Omaha. Well, let's see. Anaheim's preferred here and here, so that's 1 plus 3. Omaha's preferred and Anaheim's preferred here, so that's 3 or 7. Whereas Omaha only has this 3 right here. So again, in head-to-head, Anaheim and Omaha, Anaheim's winning. So that looks good. That's what we had in our plurality vote. Okay, now let's look at Anaheim versus Hawaii. Okay, Anaheim's preferred here. Anaheim's preferred here. Hawaii's preferred over Anaheim here. And Hawaii's preferred over Anaheim here, which gives us 6. And in this case, Hawaii is favored. Now let's look at Omaha versus Hawaii. Omaha, Hawaii. So here, Omaha is preferred. That's 1. Here, Hawaii is preferred. That's 3. Here, Omaha is preferred. That's 3. And here, Hawaii is preferred. So we have 4 and we have 6, and Hawaii wins. So in this case, Hawaii would be the Cordescent winner. So we have the same voting situation, and yet depending on how we calculate the winner, we have 2 different winners. So here we go again. City Council election, 60% Democrat voters, 40% Republican. Even though the City Council is technically a nonpartisan office, people generally know the affiliation of the candidates. In this election, there are 3 candidates, Don, Key, both Democratic, and L, a Republican. Preference schedule for the votes looks as follows. So here we have our preference schedule. We can see of the 342 plus 214 plus 298, or 854 voters who participated in this election. We can complete the percentage for first place votes, and we see that L is the winner. L received the most first place votes. So in this election, the Democrat voters split their vote over the 2 Democrat candidates, allowing the Republican candidate L to win under the plurality method with 40% of the vote. Analyzing the election closer, we see that it violates the Cordescent criteria. So if we look at this, we have L versus Don. We see that Don would win with 512. And L versus Key, we see that Key would win with 512. And Don versus Key, we see that Don would win. So Don would beat Key and Don would beat L in head-to-head. So that would be the Cordescent winner. While he had the smallest number of first place votes, he was preferred over the individual in one-on-one matchup over the other two. So this brings us to another problem. We have something called insincere voting, when a person casts a ballot counter to their actual preference for strategic purposes. So in the case above, the Democratic leadership might realize that Don and Key will split the vote and encourage voters to vote for Key by officially endorsing him, not wanting to see their party lose the election, as happens in the scenario above. Don supporters might insincerely vote for Key, effectively voting against L. Okay, example 6, I'm going to skip right now. If we need to look at more examples, we will later on. Next thing we have is something called instant runoff voting. Voting is done with preference ballots and a preference schedule is generated. The choice with the least first place votes is then eliminated from the election, and any votes for that candidate are distributed to the voter's next choice. This continues until a choice has a majority, which is over 50%. So consider the preference schedule below, in which a company's advertising team is voting on 5 different advertising slogans, A through E. This was a plurality election. Note that B would be the winner with 9 first place votes, compared to 6 for D, 4 for C, and 1 for E. There are a total of 20 votes. A majority would be 11. No one has a majority, so we need to find the winner using IRV. So, since E had the fewest votes, we'll drop E here, and this will move A up. So this will be A. So we have A, B, C, and D now. And let's see. B still had 9. D still had 6. C still had 4. Wait a minute. That's not correct. A didn't have any. So A would drop out first, as there was no first place votes. And then E would have that 1. So we lose A initially. We drop A. Now we're going to drop E. So again, this first place vote here. Okay, it can't go to A. A's gone, so it goes to D. Which means E is dropped out and D now has 7. Nobody has 11 yet. So we continue on. And we make this a D. So now C is dropped. Okay, and let's see. Here's the 4 C's. Can't go to A, so they go to D. Which then gives us D has 11, which is a majority. That's how that works. Those can get rough. Okay, we have our IRV here, and then we have same as the previous example, Goings, McCarthy, and Bunning, and Goings has 58, McCarthy had 92, and Bunning had 119, for a total of how many votes? 269. That's 150, 269, and 50% of 269 is 0.50 times 269, which is 134.5. So we need 135 votes to have a majority, and nobody has them. So we need to drop Goings, who has the lowest amount. So we start here with this 44, and that's going to go to McCarthy. And then we have this 14 here. That's going to go to Bunny. So the new total here is 133, and the new total here is 136. So McCarthy wins. And again, here we go. Another voting method on the same preference table, and we get a different winner. So what's wrong with IRV? So let's go back to our city council election. This election, Don has the smallest number of first place votes, so Don is eliminated in the first round. The 214 people who voted for Don have their votes transferred to their second choice, Key. So Key is the winner under the IRV method. We can immediately notice that in this election, IRV violates the Cordescent criteria, since we determined earlier that Don was the Cordescent winner. On the other hand, the temptation has been removed for Don supporters to vote for Key. They now know their vote will be transferred to Key, not simply discarded. So let's consider the following voting system. We have our votes. In the election, Carter would be eliminated in the first round, and Adams would be the winner with 66 votes to 34 for Brown. Now suppose that the results were announced, but election officials accidentally destroyed the ballots before they could be certified, and the votes had to be recast. Wanting to jump on the bandwagon, 10 of the voters who had originally voted in the order Brown, Adams, Carter changed their vote to favor the presumed winner, changing those votes to Adams, Brown, Carter. So 10 of these people moved to this one. In this revote, Brown will be eliminated in the first round, having the fewest first place votes. After transferring votes, we find that Carter will win the election with 51 votes to Adams' 49 votes, even though the only vote changes were made favored Adams. The change ended up costing Adams the election. This doesn't seem right and introduces our second fairness criterion. The mononicity criterion states that if voters change their votes to increase the preference for a candidate, it should not harm the candidate's chances of winning. So even though more people voted for him, he ended up losing. This brings us to our solution to that, something called board account. In board account, points are assigned to candidates based on their ranking. 1 point for last place, 2 points for second to last, and so on. The point values for all ballots are totaled, and the candidate with the largest point value is the winner. So we have a group of mathematicians are getting together for a conference. The members are coming from 4 cities: Miami, Pensacola, Tallahassee, and Gainesville. The votes were held, and here they are, right here. In each of the 51 ballots, ranking Miami first, Tallahassee will be given 1 point, Gainesville 2, Pensacola 3, Miami 4. Multiplying the points per vote times the number of votes allows us to calculate points awarded. So here we have that. See how we multiply 1 times 51, 2 times 51, 3 times 51, 4 times 51. Then we do it here, here, and here. We get our totals. We add them all up here. And looks like Pensacola is the winner. So let's go back to this election here. And let's see, we have Goings. Let's do this way. So this is 39, 80, 22, 70, 20, 14, and 44. Okay, so I have G, M, and B, D, B, and M, D, M, G, B, M, B, G, B, M, D, and simply B. So there's 44 here. So 1 times 44 is 44. 2 times 44 is 88. And 3 times 44 is 132. Here we have 14, so that's 14, 28, 42. And here we have 20 times 3, which is 60. Okay, here we have 70, 140, 210. We have 22, 44, 66. Here we have 80, 160, 240. And here we simply have 137. So now we need to go through and add them all up. So let's start with Goings. 132 plus 42 plus 60 plus 140 plus 22 plus 80. And let's see what we get. And that is 476. Okay, next up, let's do McCarthy. 88, 14, 210, 66, and 160. Add those up. And that's 538. And then we'll look at Bunny. 44, 28, 70, 44, 240, and 137. Add those together. And we get 563. So in this case, Bunny is the winner. Now, haven't we had... No, Bunny won the first one as well, so at least we got the same winner there. So what's wrong with board account? The majority criteria states that if a choice has a majority of first place votes, that choice should be the winner. So the election from example 11 using board accounts violates this criterion. Notice also that this automatically means that the Cordescent criteria will also be violated, as Miami would have been preferred by 51% of the voters in any head-to-head comparison. That's going up here. So there's 100 votes. Miami has 51. It should be the winner by plurality. And we said by Cordescent, it was Pensacola. So we have to worry. This can violate majority criterion. So next we have something called Copeland's method. In this method, each pair of candidates is compared using all preferences to determine which of the two is more preferred. The more preferred candidate is awarded 1 point. There's a tie. Each candidate is awarded 1.5 points. After all pairwise comparisons are made, the candidate with the most points, hence the most pairwise wins, is declared the winner. So this is going back to our Anaheim versus Omaha, Anaheim versus Hawaii, and Omaha versus Hawaii. So let's go back to where we did the work on this already and see what we had. Where are we? Because this is similar to the Cordescent. But what we're going to do instead is, okay, we have this Anaheim versus Omaha, and Anaheim won. So this went to Anaheim to get 1 point. This, however, went to Hawaii to get 1 point. And this went to Hawaii to get 1 point. So Hawaii wins by this method. Again, you can do just like we did with the Cordescent method to figure out who wins which one. Okay, this is the advertising groups. Determine the winner using Copeland's. With 5 choices, that is quite a long problem. Maybe if you need to see it, I'll do it in an individual recording for you, because it is a mess. Okay, here's a shorter Copeland's. We have G versus M, G versus B, and M versus B. This is going back to this same city council. So let's see, G and M. Who has the most first place votes? 44, 14, wait a minute. Okay, we're doing more preferred, so it's not just first place. So I'm probably going to need more space. Is G is preferred over M here, here, and here. That's 20. Not here, not here, not here. So that's that same 78. M is preferred over G in this 70, in this 22, and in this 80, which is 172. So that's 1 point for M. Okay, now let's look at G versus B. G is, of course, preferred in these three. 44, 14, and 20. D is preferred here. 70. B, B, and B. So this is 148. Now let's look at B. B is preferred here, which is 22. Here, which is 80. And here, which is 39. So we have 141. That gives a point to G. So G now has 1 point. Okay, last pairing. We have M versus B. M is preferred here. That's 44. B is preferred here, so that's 14. Neither of them is preferred here. M is preferred here, plus 70. M is preferred here, 22. And this is 136. B is preferred here, 80. B is preferred here, 39. And this is 133. So in this case, M is the winner. M gets 2 points, so M wins. And that's how that's done. Like I said, if you feel you need it and enough people ask about it, I'll go back to this one and work it in a separate recording. Having that many choices is going to take a while to do all the different combinations. So what's wrong with this method? Well, a committee is trying to award a scholarship to one of 4 students. Anna, Brian, Carlos, and Dimitri. The votes are shown below. Making the comparisons, we find C is the winner with 2 points. So Carlos is awarded the scholarship. However, the committee then discovers that Dimitri was not eligible for the scholarship. He failed his last math test. Even though this seems like it shouldn't affect the outcome, the committee decides to recount the votes, removing Dimitri from consideration. This reduces the preference table to this. Looking at the head-to-head, we see that A has 1.5 votes, B has a half point, and C has 1 point. So suddenly Anna is the winner. This leads us to another fairness criterion, which is the independence of irrelevant alternatives criterion. If a non-winning choice is removed from the ballot, it should not change the winner of the election. Equivalently, if choice A is preferred over choice B, introducing or removing a choice C should not cause B to be preferred over A. So, what's the fair method? Well, according to Arrow's impossibility theorem, there isn't one. It states roughly that it is not possible for a voting method to satisfy every fairness criterion that is discussed. So notice here we have another election. No matter who we choose as a winner, 2/3 of the voters would prefer someone else. This scenario is dubbed Cardesset's voting paradox and demonstrates how voting preferences are not transitive. Just because A is preferred over B and B is preferred over C does not mean A is preferred over C. In this election, there is no fair resolution. So the trick here is none of them are fair. The fairest you can get is by making it known in advance how a winner will be determined. This brings us to something called approval voting. We have a group of friends trying to decide which movie to watch. 3 choices are provided, and each person is asked to mark an X with movies they are willing to watch. So here we have our table. So we tally it up by adding across all the X's for each movie. And here we get Titanic received 5, Scream received 6, and The Matrix received 7. So in this vote, The Matrix would be the winner. So let's go back to our mathematicians. We're going to have the conference. So again, we've marked our preference table and we're going to add across this way. So here we have 30 plus 10 plus 15 plus 5, which is 60. And if you remember, Pensacola won this by one method, Miami won it by another. Okay, next up we have Pensacola, 30 plus 15 plus 20 plus 15 plus 5. So that's what, 30, 45, 65, 70, 85. Looks like Pensacola may win again. Tallahassee, we have 10 plus 20 plus 15 plus 5, which is 50. And lastly, we have Gainesville, 15 plus 15 plus 5, 35. So it looks again that Pensacola is the winner by preference balloting. Okay, so what's wrong? Or not preference balloting, but approval balloting or approval voting. So let's consider the following schedule. Okay, so clearly A is the winner. A is preferred first choice 80. Very obvious. So now suppose that the election was held using approval voting and every voter marked approval of their top 2 candidates. So in this case, 80 would receive, or A would receive 80 ballots, or 80 votes, because nobody else preferred it. B would receive 100 votes, because B is either first or second in all of them. And C would receive the 20 votes, second here, first here. So in this case, B would be the chosen item, chosen candidate. So as I said, you can see that there truly is no fair voting method, completely fair anyways. And as I said, the basic way or the best way to have the fairest you can have of a voting issue is to make sure that everybody understands how the winner will be determined in advance. So that is it for this chapter. You guys have a good day, and I will see you next time.